able to expand on what you talked about last year and bring us up to date on what can be done and what potentially can be done in the future with the various modules. I know Sam mentioned briefly earlier on the fact that a course was run at the day before the convention in Milton Keynes last year, and all of those that attended were extremely enthusiastic after they'd done some practical activities. So, Heather, if you are set,
I'm going to try.
Set.
I have, for those who know Windows, I don't have a bar at the bottom that lets me run programs, which is not a good start. But
certainly those that went on the course built something. What were there? 15 on the course? Or
yeah, 15 I think we had.
So there's a full-day event at the day before the convention, and no, there were several people. Several people came and thanked me as the organiser of the convention, which I took as a great tribute. John Worsnott, who's taken all the money and gone sailing, as you know, got quite upset that they were thanking me, and I had little or nothing to do with it, but I'll take the plaudits on behalf of John any time. So, hence, standing up early to talk about the money. And Heather is still struggling. She's got a lot more on that screen than there is on that screen. I'll tell you that.
Let's try that and see if it will come up over there. Oh. Okay.
Heather, all yours.
Okay. Well, thank you very much for your patience. Windows 10 has done it to us again. But okay, so I'm going to do two halves to this presentation. The first one is a little bit of a recap on what I said before with some relevance to what we're doing here. And then I'm going to do a little bit on building an FM radio. Well, actually, you're going to do a little bit on building the FM radio. Some SDRs. I think probably most people are familiar with a lot of these now. This Lime SDR Mini, 140 quid from the BATC shop. That's what I'm using. That's what I got plugged in here. 30.1 megahertz of bandwidth. This one, the full Lime SDR, is 60 megahertz of bandwidth. So everyone who says that HF is baseband, well, it is, and so is half of VHF and the whole of MF and half of, yeah, okay, we'll not go on. But it's very affordable now, right? We've got Pluto 130, Lime 140, and if you want to receive only £6. So hopefully we'll inspire some people to go a bit further. And I can... Okay, so the big difference between SDRs, most SDRs, and a normal analog radio is this idea of the IQ modulation. So I'm just going to cover that very briefly. The old style, we mix two frequencies, our local oscillator and our IF, and we get the sum and the difference, which means you've got a filter. It's a bit of a problem. The new way, we introduce a new term. So we have the cosine and the sine of both of the items, of the things we want to mix. And when we add them, we get the difference, and when we subtract them, we get the addition of the two. So that means on paper, and I'll emphasize on paper, we don't need to worry about our image because there isn't one. So graphically, we have a 90-degree phase shift to get the sines from the cosines. We feed in our signals and we get our I and Q, which one is cosine, the other is sine. And that, once we can do that in hardware or software, we can do a lot of good things. In pictures, just to make it obvious, we have an IF, we have a local oscillator. Normally when we mix them, we get the sum and the difference. Doing it this way, we've got our 90-degree phase shift, so we've got our sine and our cosine. We mix them with the same thing again as we had before. and now we get the difference if we add them, and we get the sum if we subtract them. So that's all done in Excel. I've said before, Excel is a fabulous engineering tool for microwaves. And hopefully, yeah, okay. So this has introduced the concepts of I and Q. So we represent a signal with two data streams, two samples. This is different, obviously. In an analog world, you have a signal, a voltage or a power or whatever. In the digital world, we turn everything into I and Qs. And half of the problem, as we'll see, is switching between the two. The other half of the problem, and this is, you only have to learn these two things and you can do all of this, is this idea of sampling and the sample rate. So here I've got an example. I've sampled here and then here, well actually more than one sample here and then here. So my A to D in this case has just got 9 levels, and I'm sampling 1 kilohertz over a 1 hertz signal. So hopefully everyone's familiar with the idea of sampling. That's what we've got here. This is talking about the decimation process, which is the way we get really good quality data out of a 7-bit converter. So that little blue RTL, it's a 7-bit ADC in that, which if you've ever heard 7-bit audio is absolutely rubbish. But because we can do this, and we'll go through it in a minute, we get a lot more bits. So here's an example. We've got 9 possible levels. We've sampled it at quite a high rate. If we then take a moving average filter of it, we get a much smoother result. And then if we resample that, so now we have 100 samples a second instead of 1,000. So we've gone down a tenth of the number of samples. But because we filtered it, we've now got a much higher resolution. And you can see we've got 42 levels in that example rather than 9 in the earlier one. So when you imagine doing that, going down from megahertz to kilohertz, you've got 10 more bits of accuracy. You're dividing by 1,000, and 2 to the 10 is about 1,000. So that's key. That's why we don't have to have a 18, 20-bit converter at the front to get useful results out of what we have in the end. Okay, so that's all the theory you need to know. GNU-radio, right? Emphasize Windows, Linux, Macs, bootable USB drives, Raspberry Pi 3s. You can run it on anything, so no one's got an excuse for not trying it out. Okay. Last time I presented it on Linux. Works well on Linux, but today I'm going to do it on Windows just to prove that we can do everything here in Windows. Yeah, okay. Well, hopefully we'll do that. That's the link, just for anyone who wants to come back to this talk later. It's very easy to install. It's just like any Windows binary. You run it, you install it, you say OK, and you've read the deal and so on. For the Lime SDR, which I'm using here, you need to download a couple of files. They're zip files, and you just copy them into the right directory. The website there tells you how to do it, and you're up and running. So you've installed everything you need to run this little guy, the Lime, and the GNU-radio. If you've got a Pluto, you just go to find the Pluto one. I haven't done it, but you can find Pluto out there. The little blue RTL SDRs, there's drivers out there for that. So very easy. It's as easy as installing anything else and as hard as anything else is in Windows 10. When you run it, and we'll do that in a moment, you get a menu bar across the top. We've got some simple things here. Search, undo, save, load, create a new one. And this is the apply power button. So we're going to design a circuit, we're going to draw it out on the screen, and then we apply power with that button, and the one to the right of it will go red, and that'll let us stop it. So if I'm going to try and present everything in terms of adding power, taking off power, everything in electrical terms, so that you can all know where we're coming from in the GNU-radio world. So here's all you really need to know. the rest of it you already know, as you'll find out in a minute. We have a graphical user interface, so we're going to draw pictures. And in GNU-radio, we draw pictures in this thing called Qt. So when you want to find out where you find a picture, say of a button or a waterfall display or anything like that, look for the Qt GUI blocks. That's the first thing. Secondly, source data. Sources give out data. Microphones, WAV files, receivers, these are all sources. Sinks take in the data, so speakers on the PC, transmitting modules. If you want to display an oscilloscope or a waveform or whatever, these are all sinks. So sources and sinks, that gets you the ins and the outs. Basically, GNU-radio is a baseband processor. So as long as your baseband, as long as your RF is less than 60 megahertz, then you can do everything in GNU-radio. If you need to do anything more than 60 megahertz, then you need a bit of hardware like this to do a final up conversion. Not quite true for the HF SDRs, but we're not worried about HDF SDRs. Okay, so once you've got your GNU-radio running, the process is you draw your circuit, block diagram is all we need here. You connect it up with data types instead of wires, as you would solder a wire to 2 points. So for this, we have to connect it up and decide what the data is. Remember, we've got to worry about the difference between I and Qs and voltages or normal samples. Then we run it, we apply power, we test it, and we play with it, and then we meet our license conditions of experimentation. Okay, so what we're going to do, hopefully, is build a FM radio, and I'm going to try. This is going to be a little bit harder now because I'm having to work over my shoulder, but let's see if we can do it. So, first off, what I want to do is build an FM radio that will transmit a 1 kilohertz tone. Everyone got that? What do I need? Carrier, okay. Keep going. Modulator.
Tone oscillator.
Tone oscillator. Power supply. Yeah. Okay, so cuddly toy, yeah. Okay, so now this is getting a little bit tricky. Fine blocks, so we can go up here, and so tone generator. Generator is a source, so we'll look at sources, and there we have a long list of sources. In this case, we'll go for the signal source, and we'll put one of them down there. And there we have a signal source. Modulator. We'll come back to the other options, but for now I want to do just a tone generator, which is a signal source here. Narrowband. FM. And we want to do a transmitter, so we pick up so far we built our tone generator and we've built a transmitter. Oh, sorry, we built a modulator, narrowband FM. And the carrier is going to be generated by this hardware because we want to do it at a reasonable frequency, not really low frequency stuff. And that is a lime, and we want to transmit. So just to recap, we generate our signal source, we bung it into our modulator, we put it up to this little guy. He takes it from baseband, i.e. below 60 megahertz, up to, in this case, I'm going to go for the 2 meter band, and we're all done. So we've drawn our circuit diagram. Now we connect things together. This is the wiring it up. obviously we want to send our modulated signal to the up converter, and we want to send the signal source to the transmitter. So we built the circuit, we wired it up. Now, remember I said about data types? Okay, so step one, let's go and have a look at this guy. Okay, I think I'm going to do this blind. So on this screen, it is asking me for an amplitude, which I'll say is 1. As long as we use a consistent set of numbers for this, it'll be fine. So it defaults to 1000 hertz as a frequency. It defaults to a sample cosine, which is fine for us. But you'll see the colour on that module is blue, and blue means it's an IQ signal. But at this point in time, we're not really interested in IQ signals because we want just to generate a sine wave, right? So we've changed that thing to a float, and I'll put that briefly on the screen. That's all I've done. I just changed this thing to a float here. I double clicked on the thing on the block, and I apply it. And okay, so now this has said it's a normal floating point number, just a non-complex IQ, and it's all connected up, and you can see that we've got an orange to an orange, which is fine. But the narrowband FM transmitter is obviously wanting to output a complex signal, because that's the way we are modulating things. We are taking in our sine wave, creating this INQ, doing stuff with it. So I'll open this guy up, and he'll open up on my screen here. And I will. So I'm going to change its sample rate. Now, we talked about sample rate earlier. It doesn't really matter for this what we're going to use. Because we're doing it on a PC and it's convenient, I'm going to use 48 kilohertz. Obviously, that's a lot more than you would normally use for your SSBs, or even 12 megahertz. Sorry, 12 kilohertz. Okay, let me fill in this other one here, which I'm sorry you can't see this. It's 480K. Right, okay. Yeah, so I'm sorry about that. But okay, so what I've changed here, I've changed the audio sample rate to 48K because this thing needs to know what it's going to be transmitting samples at to the radio. And this one is currently set to 32K, so I'm going to alter that one as well. It's a 2K deviation. You're familiar with FM deviations. And what I've said here is I want the output to be 10 times the input sample rate. So I'm taking in the signal and I'm outputting a signal which is sampled at 10 times my starts. So this is the complexity, really. This is what I was saying about this decimation thing, changing your sample rates. So where you worry about matching up TTL logic with CMOS logic or whatever in the digital world of electronics, here you have to match up rates, and a lot of the problems people have with GNU-radio is getting the rates right. So we built a signal source, which I would now quickly modify to have the same sample rate when I can find my cursor. Does anyone see? Oh, there it is over there. So 48K on there. So, okay. So now we have a slight problem in that this guy wants a lot of data. It's an up converter. It's capable of taking 30 mega samples per second, and currently we've got 480. So this is where this interesting block called the Resampler comes in. And a resampler, all it does is it takes in a sample rate and it gives out exactly the same signal but at a new sample rate, and it's called a rational, if I can spell it, a rational resampler, because it does it in a ratio, so it doesn't have to be an integer multiple of something. So I can take him out and I put him in here. Okay, so he can give you more points by interpolation. It's take 2 points, add some in between interpolation. And he can do this decimation thing which we looked at earlier. So at the moment that is doing nothing. It's multiplying by 1, dividing by 1, so it's doing nothing. Obviously what we want to do is multiply by a number, and I'm going to choose to get it up to 2 megasamples, which is a good number to use for a lot of these radios for the sort of work we do. So in order to get to 2 megasamples, I shall use my crib sheet. I multiply by 25 and divide by 6. Okay, does everyone follow why? So if I divide by 48 by 6, what do I get? Anyone going to tell me? Okay, anyway, so what I've got now is everything should tie up, and it should be transmitting up to this guy at 2 million samples a second. And I'll have my handy FM. Right, and I'm going to transmit this at 144.550.000. So 144 megahertz, and I'm going to do this at 2. So I'm now putting 2 megahertz into here. I'm getting it, 2 mega samples. I'm getting it by a 25 times and divide by 6 from my 480K, which I've got from 10K from this one. So those numbers all need to tie up, and you just need to get the calculator out and make them all work. I'm telling it to transmit on the middle of the 2 meter band. It's a 2 kilohertz deviation, and it'll be a 1 kilohertz sine wave. And if you believe the miracles of these things, excuse me, that's a little alert that tells me I've been using my computer for too long. And here's the last weird thing. This button is actually green, but as you can see, it's hardly green. And it's the most important button on the whole thing. Go figure that one. So it thinks about it a lot. It asks me to save it so that if bad things happen. Right. How are we doing for time? 12 o'clock. Have we got another few minutes, have we? Okay, good. Okay. So for anyone who followed that, you've just written your first program. You've just written a bit of GNU-radio. I know the sample rates are a bit complicated, but hopefully you can see what I've done there. I could have started with any number I liked for the sample at most SSB signals. So if I just replace this with an SSB module and I get the sample rates right, I built an SSB transmitter. Obviously a single tone isn't much good. I could have replaced signal source with a WAV file. So, and I can tell the WAV file just to keep playing. So now I've got a WAV file going up on an SSB signal to the middle of the 2 meter band. I built a beacon. Okay, this thing is capable of 3.8 gig. So type in 3.6 gig there and I built you a 3.6 gig beacon. That's it. Add PA, job done. Not hard, right? Thing is, you just record the WAV files. So you wake up one morning and you're thinking, oh, I'm fed up with CW, I'll make a beacon in something else, PSK, whatever. Just bung in a PSK decoder in there. Now you've got a PSK beacon. And that's it, you can play. I mean, you know, in what, 20 minutes we've built a beacon? Okay, I've used a good PC. This could be a Raspberry Pi. Connect that with an antenna, a PA and a Raspberry Pi, run this thing and just go away and leave it, you built your beacon. So yeah, it's not wonderful. It's not the cleanest beacon, and if you try doing this thing at 5 and a bit gigs, you'll see it wander around a bit because it's not temperature stabilized. But it's a start, right? And it's done in 20 minutes. So, okay, so that's the easy one. Now, because we're going to be pushed for time, and I can't even read what it says here. If we go over here, so down the bottom of this graph, I have pretty much exactly what we just had. Narrow band transmit up to here at the 145 with that sampler, but this time I'm feeding it from something else. And I was going to go through this, but with you designing it, but we'll cut it all a bit short, I think. So now we've got a receiver running at 103 megahertz, middle of the FM broadcast band. And I created a little box here. Remember we talked about GUIs, the graphical front end, the thing that you can actually see results from. So this is giving me a GUI range, and it has a start of 88 megs and a finish of 105 megs, stepping in 50k. This is my tuning widget, if you want to call it that. Now, because it's FM, I want to do a filter. I just grab a low-pass filter, that's it, it's done. Fill in the cutoff and the transition width. Remember, I've got my I and Q here, the blue boxes. When I've done the wideband FM receive, I've gone down to my just floating point numbers. I've put in a multiply here. Multiply for a sample is just a gain. This is an amplifier. In fact, it's a 500 milli multiplier. So this gives me a gain range of 0 to 1. And at the top here, again, another one of those little ranges. This one's just allowing me to set that multiply constant between 0 and 1. So I'm starting to build up a receiver. So what do we have here? Anyone been following? It's a repeater. In this case, it's a wideband 103 megahertz FM receive to narrowband, middle of the 2 meter band FM transmit. So I've done band hopping and I've done mode changing, and that would have taken me about 20 minutes, I guess, but we won't worry too much about it. But when we run this one, and yeah, I'll All right. Okay, now we can hear ourselves think. So, there's the radio we built. I put in a spectrum display as there because all good FM radios should have a spectrum display. You remember we had a volume control. That's this guy up here, so I can turn him here. So it's not quite the knob. John bought me a knob earlier, so so I'll interface that to my Raspberry Pi, and then we just have a really big volume control. And this bit here is our FM tune, and I'm hoping I would find a... does anyone know where there is a FM station? 102, is it? All right, where am I at? I did get one last time, which is a bit of a shame, but oh well. It would have. Oh, hang on, what's that? It's nothing. That's annoying. Windows. Yeah. Yeah. Okay. So it has locked up transmitting, but where did I set it? 145. My apologies to anyone who knows that that's out of band. But yeah, can you hear that? I'm not sure you can. Yeah. Okay. Well, that didn't work quite as well I would have liked, but the wonders of Windows and all these multiple screens running. It's all right. We just maybe have a point to rescue ourselves. Just. So a couple of things that you might remember. The SDR, obviously, it needs to get this I and Q balance exactly right. So it will calibrate itself every time. And that calibration is a bit of a problem because it blasts a little bit over bands that you don't want to be transmitting on. So we do have to find a way around that one. I'm just hoping we'll... I have a feeling that we are not going to get it to come back. But yeah, oh well. Oh, there we go. Okay. And having a GUI. There we go. Right. What frequency did people think was 10? All right. I've lost it again. No, I'm not going to succeed with this one, but you got the point. This is a cross-band FM repeater, and and when it works, as it did every time I tried it at home, I could put my handy onto the FM. It's probably Ofcom deliberately stopping me from doing something I shouldn't do. But yeah, so you get the point. In 20 minutes here, we've built ourselves a cross-band, cross-modulation repeater. We've also built ourselves a transmitter and a beacon and all the rest of it, and we've also built ourselves a receiver, and again we could bung in all sorts of possibilities for this thing. We've just done FM because it's very easy. You'll remember it's I just don't seem to be able to spell today, but GMSK, constellations, DVB-S2 and T2 for the amateur TV people, and that's just the basic modulators. Same for demodulators. There are hundreds, if I can get it. There are hundreds of processing elements inside a lot of these things. There you've got your AMs, FMs, quadratures, all the rest of it. And they're really, if you get stuck, you can write your own. And that's where it gets really interesting, but that's probably a bit advanced for what we're doing today. So hopefully you've got a handle. We can do this, we can do it on Windows, we can do in, well, 20 minutes to build a repeater, 10 minutes to build a beacon. Let your imagination run wild, please. Questions? Okay, start at the front.
Audio sync, rightmost on screen.
Yep.
Why do you need that when there's nothing coming out of it? Why is the...
Oh, sorry, the audio sync is the speakers, and that was so that you could hear it. Yeah, and I didn't really go into the details on this guy, but that's a frequency sync, a spectrum. Yep.
So within an individual block then, Heather, if you've got some parameter wrong,
yep.
What about error trapping? Is that,
Yep.
so how do you know what you've done wrong?
If you've got the data types wrong, then you'll end up with red arrows, and this horizontal bar, no entry type sign, will go red or darker red, or actually brighter red, I suppose, to tell you you've got an error. There are very few actual errors other than type errors. What probably happens is that you, for instance, if you'd got this decimation wrong, then this will be giving data out at, let's say, 48k instead of 480, and the next block will be expecting data at some other frequency, and so the second block will just sit and wait until it's given it enough data, then it'll give it out at its data rate, and obviously the audio will be all messed up and so on. So usually it's best to start simple, build something up that works, and then when you've got something that works, as we did, you bung that lot into something else and build that up, and then gradually you build up all your stuff. But it's very, very rare that you actually get any errors. It's almost always, as long as all the colours match up for these little boxes, you're good to go from a matching point of view. Just a matter of getting the rates right.
Think of it like impedance matching.
Yeah, impedance matching is very similar to getting the rates right. It's very, very similar.
Assuming you've got something that you're happy with and that works,
Yes.
can you save that as an executable so you don't have to go through this?
Sorry, yes, you didn't see that. It asked me on this screen before I ran it to save it, and I saved it. These three at the top here, this one and this one, those are saved pictures.
You can just go and run those straight away.
Yeah, and you don't need to run GNU-radio. They're actually Python scripts. So from the command line, you can just type in whatever that says, lime mini FMTX or whatever, and off it goes. So once you've built it, you can do all that straight off. John?
You said of Python scripts, is that 3.6, 3.7?
I don't know what Windows is using. It does vary, and you need to get it right. But the Windows installer and the Linux installer will get it right for you. But I'm not sure where they are at the moment. They're fairly up to date, so it probably is later versions.
Another question.
Okay.
On the line SDR, two versions of it, is it the same PCB with parts missing?
No.
Or is it two different PCBs?
The full Lime SDR, twice the price, is 2 transmit and 2 receive, 60 megahertz rather than 30 megahertz bandwidth. Completely different thing.
It's physically much bigger.
Yeah.
Is it going to be a repository of like ones that have been already designed? People want to play and have a look at it?
There are lots of tutorials online. I found that most of this is actually covered by one of the beginning tutorials for the Lime. Yes, I think, and that's something I think we're talking about doing an SDR project within the microwave group, and part of that will be this sort of thing. So we'll hopefully have some loan kit. You take away your loan kit, and you tell us, or you can do yourself, what you want it to be able to do. So yeah, there are lots of things available and more.
Heather, to answer our colleague's question, there are repositories. When you start looking, there are a number of repositories. What I don't think anyone can tell you is which are the preferred ones and where the quality is higher and so forth. So as with lots of things, it's you need to understand what it is you're looking at, but there's an awful lot of stuff out there waiting to be used.
There is, yeah.
But perhaps then there may be a case for a microwave group repository.
Yep, we're thinking about exactly that.
Of projects that's done by people in the group.
Yeah, and that would be one that you should avoid because the quality would be really. Okay, thank you.
Thank you, Heather. What you said was a repeater in 15 minutes, a beacon in 10 minutes. What you didn't say, and a license for a repeater or beacon in about 3 years. So, thank you again, and there is no doubt that, well, two things I suppose. Doing a live demo is always a challenge. But B, there is no doubt that GNU-radio is got lots and lots of way to run in terms of what the potential is. So thank you very much again for the presentation. We look forward to an update next year. Thank you. Now, we'll be 5 minutes or so whilst we change the technology back to Jason's PC before William comes and talks to us. So if we can take a couple of minutes, but don't all go away because we'll try and catch up again and get slightly back on track.
A little challenge.
Okay, thank you.